Thank you all for being here. I would thank the organizers. I'm one of them, but really thanks to Francois. He's the mastermind here who made this happen. So really thank you. It's wonderful to be here. And okay, I was a PhD student of René's, like several people here, and like even more of us, I owe him a debt of gratitude for many years of mentorship, guidance, for promoting me in my work. So really thank you, René. And to express this gratitude, I thought it would be fun to share some embarrassing stories. However, it turns out the lectures today are recorded, so this is best not to be documented, so you're safe, René. Although I will recall one time in Providence, Rhode Island, we were at a restaurant and you asked the waitress a question about the wine list, and maybe not detecting a French accent, she started to explain in great detail how champagne actually has to come from a specific region in France, and the look in René's face as she's explaining these trivialities to him, if I can avoid that face from you today, I'll know I've done an okay job here. So good. So I want to talk about a line of work I started 4 years ago or so about a very classical topic, propagation of chaos, but really focusing on getting the sharp quantitative rate of convergence in the mean field limit. And I hope to explain to you that this is surprisingly subtle and surprisingly was not known before this work. So there will be two parts to the talk if I'm not too slow. Part one will be about this classical mean field setup, and part two will be about a more recent extension to non-exchangeable systems where you break free of the symmetry baked into typical mean field models, as we got a glimpse of at the end of Pierre-Louis' talk yesterday. So let me start with the very basic setup here of a system of n particles interacting in a mean field fashion. Okay, so say these particles live in Rd. There are n of them. I should probably put an additional n index here, but I'll suppress that. Okay, and for simplicity throughout the talk, although you can generalize this, I'll take IID initializations. Okay, so this, I'm making some simplifications for the talk here. I'm putting a constant diffusion coefficient. You can generalize that in some ways, but I won't talk about this here. In mean field games and other contexts, you'd like to have more generality in the form of interaction. This is what René would call a scalar interaction, or maybe a pairwise interaction. We're really just averaging over pairwise interaction forces. In progress, the same story I'll be telling you today can adapt to these say higher order interactions or more general functionals of the empirical measure sitting here in the drift. But this case is already quite rich and contains the main ideas, and this class of models shows up in a wide variety of contexts already, particularly in the physical sciences where you think of, these could be particles exerting a gravitational or electrostatic force on each other or something of this sort. So the typical story about these particle systems is about how they behave as n goes to infinity, and this is what takes us to mean field limits and propagation of chaos. And you can describe the large n limit in terms of, well, there are a couple of ways to do it, but I'm going to stick with the probabilistic view because this is a conference in honor of René. So you can describe the limit in terms of the McKean-Vlasov equation, which I'll write as follows. This bracket means integration with respect to this distribution mu t. And we integrate in the second argument of this interaction function b. And this mu t, this measure mu t, is supposed to be the law of the solution process itself. Okay, and this is why I picked mu0 for the name of the initial condition here. This should be the same initialization for this equation here. And okay, I think many of you are familiar with this, but roughly speaking, the way you get here from this n particle system is to kind of squint and replace the empirical average with an actual expectation, imagining that a law of large numbers is kicked in. Okay, and the intuition behind that is that for any given pair of particles I and j, the interaction strength is order 1 over n. So you'd imagine that any pair of particles should be independent. And really the game of mean field limits and propagation of chaos is making that rigorous. So how really approximately independent are these particles here? Okay, so I want to explain in more detail what exactly is the rigorous way in which you connect these two things. And this is through this notion of chaos, or molecular chaos as Boltzmann and then Mark Katz referred to it. And there are two different ways, equivalent ways to formulate this. And even though they're equivalent, I want to give them two different names for reasons I'll explain. The first notion I'll call global. And this says that the empirical measure of the particles should converge weakly, say in probability, to this non-random limit mu t. So this is a mean field limit as it's often known. And this turns out to be completely equivalent to another notion that's more local in character. I say global here because this involves the full configuration of all n particles. The local counterpart says that if I take any k, let's say, any number k of particles out of the n, I fix some number k and send the total size n to infinity, then the joint distribution of k particles out of the n should converge to IID copies from this mu t distribution. Okay, so I should stress that because they're IID at time 0, the whole system is symmetric or exchangeable. So when I talk about the k particle distribution, it doesn't really matter which k particles I talk about. So let's just say 1 through k. And what I'm doing here, again, I'm fixing a bounded number k of particles and sending n to infinity, and this joint distribution should become IID in the limit. Okay, and this is local in nature, I would say, because it's involving boundedly many particles at a time. And you could say exchangeability is the bridge between these two statements. These are completely equivalent. This is often attributed to Snitman and or Tanaka. And actually, this has nothing to do with the particle system here. This is a completely general equivalence that holds for triangular arrays of exchangeable random variables in Polish spaces, maybe more general than that. But the key point I want to stress here is that this equivalence is purely qualitative. And there is apparently really no sharp way to transfer quantitative information between these two statements here. So if you have the optimal rate of convergence in some sense here, really here, it's not so clear what that implies on the local side. Now there are ways of passing quantitative information from one to the other, but they seem to lose something, particularly in this global to local direction. For one, okay, you might imagine, and it's quite popular to study this convergence by looking at a distance between this empirical measure and its limit, say an expected Wasserstein distance. And even if we were in the better case of IID particles, the expected Wasserstein distance would suffer from dimensionality of an underlying state space. It would be something like n to the minus 1 over d. And the sharp local rate that I'll show you soon actually doesn't have a dimension dependence. So there's no way you could really go from here to here in a sharp way if you're thinking in terms of expected distances of empirical measures. Another approach that's more common in the PDE literature on this subject is to use some form of subadditivity inequality. And there's a version for relative entropy and for various other distances like quadratic Wasserstein distance. So let me state it in this form first. If you look at the squared distance between the k particle joint distribution and its IID limit, you can bound this by k over n times the full n particle distance. This is again due to exchangeability, and it's kind of intuitive. The distance, or maybe energy if you like to think of it this way, contained in k out of the n particles can be no more than its uniform share k out of n of the total. Okay, so what can you do with this? Well, if you're able to get a good bound on this global quantity, this n particle distance, then you can transfer this to a bound on the k particle distance. Now, the full n particle distributions can't converge together. This distance will never go to 0. I still haven't found a really concise, convincing explanation of why that can't go to 0. It just never does in these models. At best, you can hope to bound this quantity uniformly in n. Okay, and if you get, say, an order 1 bound for this, you get an order k over n bound for this left-hand side, for the square distance. So it's not exactly written in this way, but if you open this classic monograph of Snitman, this is essentially what's going on in his proof of propagation of chaos. In the case where B is Lipschitz, there's this very nice coupling argument, which was one of the first things Rene had me read when I started working with him. And this is really the nicest entry point to the subject, I think, for someone who's new to the field. It's a very, very nice stochastic coupling proof. And behind the scenes, this is essentially what's driving things here. So you can deduce propagation of chaos from this global estimate combined with subadditivity. Okay, now more recently, there is a really beautiful pair of papers from Jiabin and Wang looking first at the case where this drift is just bounded and measurable with no continuity whatsoever, and then a very influential follow-up paper looking at a class of singular interactions, which are very relevant in physical models. And I won't go into the details of what this means. Basically, B is the divergence of some bounded vector field in the distributional sense. And they used relative entropy instead of the Wasserstein distance, but with a similar, with a similar subadditivity kind of concluding things for them. They look at the relative entropy between these two measures, time differentiate it, and do some very clever analysis to bound the time derivative of the n particle entropy in terms of itself, and then do a ground wall argument to close the loop there. So there's a really nice pair of papers from 2016 and 2018 that really popularized relative entropy methods in this business. Okay, so this is right. A good. I should mention there are plenty of other methods and results on quantitative propagation of chaos. I think these are kind of representative, and even beyond these examples, the sort of central message here is that really the methods before what I want to present are really global in nature, studying the empirical measure or something about the full n particle distribution, and it seems that you can't really get the optimal rate at this local level by working with global objects. So the theorem from a few years ago, from a paper of mine from 2021, looks at the relative entropy, which I'll abbreviate as hk of t, because I'll talk about this a lot. So again, between the k particle distribution and its IID limit, this actually you can improve to be order k over n squared. Now, I'm not going to give you precise assumptions. This works in the case of Lipschitz drift or bounded measurable drift and a broader class in the paper, but I don't want to give the fully general assumptions. And not only can you improve this to k over n squared, whereas it was only k over n in these examples, but this k over n squared is actually sharp. You can't improve this anymore. And the reason you can't improve it anymore, well, you can see this from working with an explicit example. So I'll tell you what that is in a moment, but I should mention that this came as something of a surprise. I did not kind of set out to improve this rate to k over n squared. There were papers before saying that this k over n rate is widely believed to be optimal. So I kind of was doubtful at first, but to convince myself, I realized if you take the drift function b to be linear, then all of the processes become Gaussian. You can explicitly identify these distributions and compute these distances and really see that you get k over n squared. So the Gaussian example shows you that this is sharp, that you can't improve this in general. Now, let me mention there's been some nice follow-up work on this since then. So by myself and some other authors as well. This big O constant here is hiding dependence on the model parameters, say the Lipschitz constant or L infinity norm of the drift B. It's also hiding a dependence on the time, which typically grows exponentially in time. But if you're willing to impose some stronger assumptions, then you can improve this to uniform in time estimates. That was a follow-up paper with my student Luc Laflemme. There have been a couple other follow-up works. I want to mention in particular a very nice one from Songbo Wang, who's here, that basically married my method with that of Jiabin and Wang to cover this singular class of interactions. So this, I was getting many questions from the PDE folks, oh, can you handle singular interactions? And the answer was always no until last year when Songbo had a very nice idea in this direction. So I want to spend some time explaining some interesting ideas of the proof of this theorem, and then I'll explain the extension to this non-exchangeable case here. Feel free to interrupt along the way if there are questions. I don't mind. Okay, so the proof starts from a combination of two ingredients that are kind of nice tools that I've been using in other contexts for a while. One is, how do you estimate the entropy the relative entropy between two SDEs? And maybe I should stress Markovian SDEs. And the nice thing about working with relative entropy when you're comparing SDEs, at least with constant diffusion coefficients, is that the entropy between the two SDEs becomes the L2 squared distance between the drifts, essentially. So entropy puts you in L2 territory, and L2 is, of course, the nicest norm to try to estimate things in. So I'm not going to give the details there. There are two ways to see it. If you work with the time marginal distributions as I've written it, pt and mu t, then you need to do some calculus. But if you work with the path space distributions, this is a very nice application of Gersanov's theorem. That's quite a well-known calculation. Now, the second ingredient you need here is the Markovian projection, or aka mimicking theorem, that tells you that how to write down basically a self-contained kind of Markovian dynamics for an SDE system that wasn't Markovian to begin with. And the way we do this is to apply it to the, say, first k out of the n particles. So we view the remaining particles, k plus 1 through n, as just some additional source of randomness that we'd prefer to forget about in order to just identify how the k particle distribution is evolving in its own right. Okay, now the magic that happens when you do this is that you basically get to take the drift of this smaller collection of particles and replace it by its conditional expectation given those particles. And this gives you a new process that has the same time marginal distributions. Okay, and the magic that happens here is if you look at this new drift, let's call it b hat, for the ith particle in this subcollection. Okay, again, you obtain this by taking the conditional expectation of the real drift, given these first k particles. And this simplifies in a nice way, okay, because the first k terms in this sum are actually measurable with respect to what we're conditioning. So we pull those out. And this gives us we get a sum of k terms, and I'm going to multiply and divide by k to write this as the empirical measure of the first k particles, integrating this function b in its second variable. Then the remaining term is k plus 1 through n. There's some actual conditional expectation happening because we have a particle here that's not in this list here. But because of the symmetry of the system, all those conditional expectations are actually the same, whether we put particle j equals k plus 1 or k plus 2 up to n. Those are all the same conditional expectations by symmetry. Okay, so we have n minus k of those terms. So we can write this as, I'll write it in this same kind of style of notation, we take the conditional distribution of one more particle given k particles and use that to integrate b in its second variable. Okay, so this is, when you do this Markovian projection, you now can identify a sort of self-contained dynamics for the k particle marginal, but it's not really self-contained because this drift depends on the joint distribution of k plus 1 particles. Okay, so this leads you to at least a probabilistic viewpoint on what physicists and analysts know as the BBGKY hierarchy. These are the initials of 5 physicists. And you can derive this in PDE terms. You have Fokker-Planck equations in place of SDEs. But what I like about writing it in probabilistic terms is that we're used to thinking as probabilists in terms of conditional distributions. And when you do this, it kind of makes the remaining analysis jump out at you a little bit more. Because when you plug this into this entropy estimate, we end up comparing this whole drift with the McKean-Vlasov drift, which basically takes the same form. We're integrating over some other measure, the same function b. Okay, and if we want to compare, say, this integral with this one, for instance, we can bound that in terms of a distance between mu t and this conditional measure. And when you do this, I'm going a bit fast here, but I'll come up for air soon. When you do this comparison, you can bound this in terms of kind of the entropy itself and sort of close the loop a bit. Maybe I'll move over here. So a kind of key point here is that when you, say, compare these integrals under these two distributions, the conditional one and the McKean-Vlasov, if you have a function that's, let's say, bounded, then you can bound this by the norm of the function squared times the total variation distance between these two measures. And that in turn you can bound according to Pinsker's inequality by the relative entropy. And I'm going to put expectations everywhere here because we're still conditioning on this random variable here. And what we're left with is an expectation of a conditional entropy. And if you've worked with relative entropy a bit, then what might jump out at you here is the chain rule for relative entropy that tells you this expected conditional entropy is exactly the entropy increment. So the k plus 1 particle entropy minus the k particle entropy. Okay, and this is kind of the magical part of the argument here that I only know how to do with relative entropy as opposed to any other kind of distance on probability measures. It's because of this chain rule, this very special property for entropy. Okay, so that got a bit into the weeds, but I want to kind of emerge and summarize where this line of reasoning leads you, which is to sort of a key system of inequalities. So we start from the relative entropy of k particles and compute the time derivative. And at the end of the day, this is bounded by two terms. And I'm going to ignore constants here. We have a k cubed over n squared first, which is small if k is much smaller than n. And then we have this entropy increment term. And we have k terms here because this is what happens when you do the entropy. You get the norm of the vector of the drifts of k particles. We have order k terms here. So this is for k smaller than n. And at the top of the hierarchy, we have a bound of order n, which is really quite useless on its own. But what's interesting is what happens as we work our way down the hierarchy to smaller and smaller k, because then these terms become quite small, and we need to understand what's happening with this entropy increment term. Okay, so this is sort of, this comes from this hierarchical approach where, again, the k particle distribution depends on the k plus 1 particle, and so on and so on. And at this point, you can kind of forget about the entire stochastic process that we began with. This is a pure analysis, real analysis problem. We have n functions of time, h1 through hk, that satisfy this system of differential inequalities. Now, how do we extract some information from this to get to a final answer? And this is actually not kind of immediately obvious. My initial paper here had a sort of not too hard, but kind of tedious, like 8 or 10 pages of calculation where you do Gronwall's inequality and then get all these nested integrals you have to deal with. A referee suggested an inductive argument that's much shorter, but I don't fully like it because you have to kind of know the answer in the first place. It's a, say, guess and check kind of approach. More recently, really because of the work on the non-exchangeable case, I've arrived at what I would say is the nicest proof in my view. And it makes me hear the echo of my advisor's voice telling me to think probabilistically here. If you're having trouble understanding some kind of analytic object here, let's think probabilistically. So what happens here, if you kind of squint at it, is this is a linear system of differential inequalities. If you collect h1 through hn as a vector, then coordinate-wise you have an inequality here, where I'll write C just for this vector of these numbers as k varies from 1 to n. And then we have some matrix times the vector h showing up here. This is clearly linear in h. Okay, now what is this matrix A? This has a very nice, simple structure. We have mostly zeros and just a bunch of things on the diagonal and just above the diagonal. Okay, and if you like to think probabilistically, you'll recognize this is a rate matrix of a continuous time Markov chain in the sense that it's negative on the diagonal, non-negative everywhere else, and the rows all sum to 0. Okay, so this is a rate matrix. What's the Markov chain? The Markov chain associated with this is called the Yule process, which I'll call YT. And the transitions are from k to k plus 1 at rate k. So this is a well-known counting process, and it's kind of a classical growth process in the sense that you imagine like an evolving population size where you have an amoeba that has an exponential clock, and when that clock rings, it divides into 2 amoebas, and then each one of those has an exponential clock, and when that rings, it splits, and so on and so on. The population size at time t follows this Markov process. Okay, so I should stress that I'm just introducing this process as a tool for encoding understanding the structure of this purely deterministic object here that we arrived at. I don't have any other reason to say that this process has anything to do with the interacting particle system that we started from. It's just a useful tool now to understand this hierarchy here. Okay, so once you recognize this rate matrix here, well, what happens is if you change this inequality to equality, this would be exactly a Feynman-Katz formula for this Markov process. With inequality, the same argument goes through just with an inequality, and as a result, you can bound these things in terms of expectations involving this Markov process. So whatever this vector C is, you plug in this Markov process here, and this was really just 1 over n squared, and we have this Yule process cubed now. And this k means we're starting at value k for this Markov process. So the k particle entropy, we've now bounded in terms of an expectation of this stochastic process. And there are various ways to finish the story from here. You can open up a book with properties of the Yule process. This has a known exact distribution. This is negative binomial. So you can read off moment bounds for that, or you can kind of work with the generator and do this analysis by hand. And this gives you the final answer of k cubed over n squared, which is not actually the right answer. I told you k squared over n squared. There's a last step to do to shave off a factor of k, but I'm going to skip that part here. Okay, so this was the rough sketch of the proof for this mean field case. And in the last 10 minutes here, I'll explain how to adapt some of these ideas to the non-exchangeable setting. Any questions here before I go into that? Yeah, Frederick.
With we couldn't shave off that last factor of k, would everything fall apart after that?
No, I mean, this is still a useful bound. I mean, this has the right order in n, which is the more important variable here. But you know, the optimal one is k squared. So, and it's not too much more work. Okay. So the part 2 of the talk will just vary the setup of the model a little bit, where instead of the uniform 1 over n weights in the initial SDE system, we'll replace them with some general weight matrix that I'll call J. But otherwise, the setup is the same, IID initial positions, and okay, the matrix J, what should we assume about it? Non-negative entries is convenient. There's been a lot of literature on these kinds of models in the past decade, including some work by Rene on extending mean field and mean field game kinds of models to these sort of asymmetric setups where we want to, you know, you can imagine trying to enlarge the scope of applicability of these models. And mathematically, the challenge is to see what kind of tractability we can maintain from the mean field setting or sort of port over. And as soon as you introduce this maybe small looking change, you get a lot more complexity because you lose exchangeability, you lose symmetry right away, and a lot of tools go right out the window when you break free from exchangeability. So I'm going to give a glimpse into this story under a restriction here that's not in the paper, but it's convenient, kind of saves me from having to explain more stuff than I have time for. I'm going to assume the row sums of this matrix are all equal to 1. So kind of the total size of interaction felt by each particle is uniform here. You can go beyond this case, but what's nice about this case is that there's sort of a universality phenomenon that shows up, and this is due to other authors. And this says that basically if you're given now a sequence of models where the size is growing, where n is going to infinity, and you have this row sum equal to 1 along the way, then the limit, the mean field limit is again going to be McKean-Vlasov. You don't have to find a new limit. You get the same McKean-Vlasov limit in this case. This is not obvious, and this is really a powerful result already that says we can go well beyond the complete graph the mean field case, and this wide class of models will still give us the same limiting behavior. I should issue an important caveat here, which is that this works in sufficiently dense situations as opposed to sparse situations. So there's this kind of McKean-Vlasov limit only comes up if you're dealing with a dense network. Now I'm talking about a matrix, not a network, but a good example to have in mind is when there's some graph behind the scenes, some network on your n labels, with your n particle labels being the vertices of your graph, and your matrix would tell you that you should average uniformly over your neighbors. Okay, so ni would be the number of neighbors of label I. So this is a kind of natural class of examples to keep in mind that fits this condition. And if you want the McKean-Vlasov limit, you need the degrees, you need the neighborhood sizes to diverge in some sense. And part of what's interesting mathematically is to get a handle on exactly, really precisely what dense means. Okay, if you want some phenomenon to hold, like convergence to McKean-Vlasov, then exactly quantitatively what kind of networks do you need? You know, how dense does this need to be in some sense? In what sense do the degrees need to diverge? Okay, so this is kind of the setting, the background here. I should erase, make some room here. And again, the goal is to try to understand some sort of analog of what is a mean field limit in this context. Now, if I didn't make this row sum simplification, a first challenge would be to figure out, well, what should we converge to instead? What's the alternative from the McKean-Vlasov limit? And that's a whole separate story, but there's a kind of non-asymptotic construction you can do there, even if you don't suppose some sort of graphon structure. And I have a separate paper developing that a bit on its own about what I call the independent projection, which really allows you to adopt a very non-asymptotic viewpoint on this whole business without assuming you have a graph-on limit or anything of this form. So that's just a brief plug for what's going on there. Let me just briefly sketch kind of how this whole hierarchical approach adapts to this context, and then I'll wrap up. So, okay, that was a kind of first issue, but we're just going to assume that we're in this McKean-Vlasov world, so we don't have to identify a different scaling limit. The second kind of issue we run into is that if we try to think about, what the marginals are doing here, we can't just talk about the law of k particles anymore, because which k particles we choose, might result in a different distribution. So now the marginals we need to index by sets of labels instead of just numbers of particles. But okay, once we embrace this additional complication, we can try to adapt the previous argument. So I'll again look at the relative entropies between these marginals and the IID McKean-Vlasov competitor. And you can kind of follow your nose and carry out a similar sort of analysis. There's this Markovian projection idea, and now it's a bit more complex because, previously the k particle distribution depended on the k plus 1, and so on and so forth. Now the let's say V marginal will depend on the V union J marginal for all J not belonging to V. So for every set, you need to look at all of the possible next particles you could add in to the set. And that will kind of give you a kind of more complex sort of hierarchical structure. But nonetheless, you can calculate and estimate these time derivatives in a similar way, and you get two terms. One of them, I'm again just going to abbreviate as C, and maybe I won't even say much about what that is. The second one is the more interesting term, where we again have an entropy increment, but we need the sum, again, over all of the possible next particles we could add into the set. This CV is kind of a measure of the internal connectivity of the set. It's just some quantity involving J, but I don't want to say too much about that, so I'll leave this undefined here. The interesting part is this A, which is proportional to the sum of incoming weights from the current set V into the next possible label J. And this, again, when you look at this whole hierarchy of differential inequalities, which is now much more complex, it's indexed by sets. So this vector H is of size 2 to the n now. But this again satisfies a linear system of inequalities, and the matrix multiplying H on the right-hand side again has the structure of a rate matrix of a Markov process, precisely because this entropy increment is appearing here. Now this Markov process that shows up is equivalent to several things that have been studied before. We call it the percolation process because it's equivalent to the neighborhood process in first passage percolation. This is also equivalent to what's called the SI model in epidemiology, not SIR, just SI. So this is a stochastic growth model. The set is growing one site at a time randomly. So once you become infected, you never recover in this model. So you're just randomly growing until you've reached all n particles. And once you understand things in terms of this process, let's call it xt. So again, I should say the rate of transition from a set V to V union J is precisely this number AV to J. So you're growing one element at a time in this set. Once you recognize kind of hidden in this object the structure of this Markov process, you can turn this hierarchy of differential inequalities into a bound just in terms of an expectation involving this Markov process, initialized at whatever set V you're trying to compute your relative entropy on. So this again has the same structure as before, just now with this more complicated Markov process showing up. And then once you're here, we have this completely different stochastic process, the one we started on, and the game is to estimate these expectations. And there's a good deal of work that goes into that I'm not going to discuss here, but and I think this method is more interesting than the actual results, but I should give you some actual concrete results that come out of this. And maybe I'll specify to this graph case just to make it a bit more concrete. So this graph case where we have an average over your neighbors in the network. There are two concrete results I'll state that you can derive from this representation here. If I fix some number k of particles and I want to look at which collection of k particles is the farthest from the IID McKean-Vlasov. So I look at the worst case entropy over all k particle collections. This you can bound by k squared over the minimum degree squared, the minimum neighborhood size. So if you're in the mean field, the complete graph case, this is just n, and we get back the k over n squared. Now, if you're a bit more forgiving and you don't need the worst case to be kind of close or converging, if you just look at the average case, so you allow some of the k particle collections to be maybe very bad, maybe far from their limit, then you get a nicer rate where instead of the minimum degree, you get the average, let's say, reciprocal of the degree. Okay, so what's interesting about this is you now have two different kind of quantitative notions of how dense the network needs to be in order for these measures of how close you are to McKean-Vlasov to be going to 0. Okay, so this first one says if you want the worst case distance to go to 0, you need the degrees to diverge uniformly. The second one says if you only care about the average case, then you only need the degrees to diverge somehow in probability, like a typical degree is diverging. And maybe some of them are quite bad. And if you like to think concretely in terms of the Erdos-Renyi graph, let's say, then the difference between these two in the Erdos-Renyi graph, the first one would require, okay, for the minimum degree to diverge, you need the neighborhood size to grow faster than log n. Whereas if you just want this kind of typical degree to diverge, then NP just needs to diverge the neighborhood size at any rate. Okay, so doing this sort of quantitative study gives you precise notions of denseness that tell you when these kinds of limits hold. And you can go further with this, but I think this is a good place to stop. So let me thank you all for your attention and Renee for staying awake the whole time.